All right.
Thank you very much. This talk will be on MALintent, which is a coverage-guided intent fuzzing framework for Android. So just to motivate the work a little, because Android has such strict app isolation, every single app runs as its own user in Linux, so there's not much that apps can do to each other without going through the OS first. So the IPC mechanisms between these apps becomes like a key attack vector. And as we can see in this graph, the number of sort of attacks related to IPCs and intents, the CVEs, are on the rise. So just as a quick motivating example to show like what these sort of attacks can actually do, this is an example of a bug we found in Chrome, where an attacker app could send an IPC to Chrome, and Chrome would end up leaking cookies, browser state, a visual dump onto the file system, and the attacker has access to your entire browsing history, everything you're logged into, etc. So with that in mind, let's talk about intents, because they're one of the primary sort of IPC mechanisms in Android. If you're in Chrome and you want to share a photo to your Messages app, you can long tap it. What that actually ends up doing underneath is it creates this intent object with an action of, let's say, share, and has that image attached with it, and then it goes on to the other app. So these actually go across the app boundaries. So inside of these intents, there's the action, which we saw, like share. There's also usually some metadata. So for example, if there's an intent to send an email, you may have the email address pre-filled out so that it's already in there in the email app and you don't have to fill it out yourself. These apps can basically use these intent to launch other applications. So for example, not every app needs to implement like its own mail sending protocol, for example. You can just launch Gmail or whatever your preferred mail application is just by setting up this intent, saying like, okay, it should send an email, it should have this subject title and this attachment. And then once the app launches this, it'll actually launch your preferred mail app to do that. And normally these intents sort of, they launch another app and then they'll ask you like, okay, do you actually want to send this email or not? They kind of act as like a pre-fill out this information sort of thing. And these intents, because they're so structured, are kind of the ideal like base point for fuzzing, because they have these fixed like metadata, they have these actions, and we can kind of manipulate them and see what sort of behavior we can invoke in these other programs. So going on that basis, MALintent is basically a three-step sort of design. So first, we actually gather from the app, the APK, we rip apart like what sort of intents it can accept, what the metadata it takes is, and we use that to generate an intent specification. So let's take a look at that. We take this metadata from basically two parts. There's the manifest where you have to declare what intents you expect, and then the app code actually has what you do with that intent. And we use that to generate this intent specification to start the fuzzing process. So the manifest is pretty simple. It basically just declares statically like, okay, I want to be able to handle the send intent, and I can handle mails, for example. This kind of lets us generate this sort of JSON blob that defines what the intent structure consists of, and this is what our fuzzer uses as like a baseline to start fuzzing with. After this, because we want to explore these behaviors in a systematic way, for the fuzzing, we need sort of coverage instrumentation back. I won't go into too much detail on this. We did kind of make a new cool technique for Android coverage instrumentation using basically like the Java debugger APIs, but that's detailed in the paper. For now, let's assume that we've been able to instrument the app for coverage. So after that, we start our actual fuzzing loop. So we take that initial intent specification, that JSON blob we saw. We use it to generate intents, we send them to the device, and mutate and explore deeper and deeper behaviors. It's like a traditional fuzzing loop. The key thing is MALintent has a couple of different bug oracles that it's looking for when it does this fuzzing. So crashes, those are kind of obvious. These can be bad. For example, if someone can crash your dialer app, they can prevent you from dialing 911. They just repeatedly do that. But they're also extremely common in most Android applications. The two sort of interesting ones are the privacy violations and memory safety violations. So let's first take a look at the memory safety issues. So while Android apps are mostly written in Java, a lot of the times app developers want to leverage these C and C++ libraries. Like you may want to use FFmpeg to like convert videos, or you may want to use OpenGL to render like your game engine. So a bunch of these apps will actually use a decent amount of native code inside as well. And interfacing with these native libraries is done with the Java native interface. And in this, you basically declare like a stub on your Java side, and when you call it, the JVM takes care of like going in and calling the C side for it. So our basic traditional fuzzing loop that we had works to sort of explore these JNI behaviors, but it's a little bit slow because you have to first send the intent, it has to go through the OS, then it has to go through the app, and then finally it goes into the native code. So sort of to look at one of these JNI calls and how it actually ends up in Java, a lot of the time it won't just be like an entry point you call and then control flow is transferred over to the native code. A lot of the time the Java code has like these data flow dependencies. Like you may call like an open file function, it returns a pointer, and then you have to send it to this other function. So there's these complex data flow dependencies that end up being created on the Java side. And the key sort of insight that we had was that when we're doing this fuzzing, we get these dynamic traces that show us what these data flow actually look like. And what that lets us do is it lets us synthesize basically a harness that just exercises the native code based on those data flows that we saw. So in that open file into read frame example, we just basically synthesize a fuzzer that directly calls those two things. And this allows us to basically do fuzzing at a much faster rate on these native libraries. And using that, we were able to find this example bug in a image library that's used by Facebook apps like Instagram. There was basically just an off by one when they're rounding off the images. They made like a buffer too small. The other main oracle we have is the privacy violations detection. So this is sort of similar to the one I talked about in the start regarding the Chrome one. So a lot of the times, because intents, one thing I didn't mention, intents are not only IPC, they're also intra-process. So when your own app wants to call another part of your app, that's also using intents. And a lot of times what happens is developers will leave around these code paths thinking only my app can access it. But in reality, it can be accessed by an attacker if they know what metadata to put in there. So for example, let's say you have a camera app that accepts the path on where to store the file. Well, now an attacker can say, ask it to record video and retrieve that video without ever having camera permissions itself. That's one example through the file system. One other example is, this was one, the permission escalation one, for example, was a common problem in camera apps where you could set, say, a timer to take a picture in, and it would take a picture after 5 seconds and send it back to the malicious app. Normally, when you say, okay, I want to take a picture with your preferred camera app, it'll launch the camera app, but you actually have to take user interaction to press, okay, I want to capture it before it'll actually give it back to the other app. But in this case, by using the timer, attackers were able to just force the camera to take a picture and send it back to them, effectively giving them camera permissions without having them. Another sort of common one is, let's say the dialer app. Apps can set up like a phone number to call, but ideally all it should do is open up the dialer app with the number pre-filled in, and you still have to press the button. But we found, for example, bugs where apps would basically initiate a call without the user's consent, and now if they call a number they control, the attacker has access to your running microphone, basically. So these sort of privacy violations are really like key to detect, and we use dynamic taint analysis to find them. So we take a bunch of these sensitive data sources like your GPS location, information from your camera, information from the internal database of the app. And if it can sync into like the file system, or if the intent can control which part of the network it goes to or what file it goes to, then we consider that to be a privacy violation because the attacker can basically control where the sensitive information is going to. For our evaluation, we ran against 500 apps from the F-Droid dataset, which is a bunch of open source apps, and the Google Play Store's top 50 overall and top 50 productivity apps. We gave each app a 16-hour round of fuzzing. And the results are that we were able to find 9 privacy violations in pretty mature apps like Chrome and WhatsApp. A lot of crashes, 49 of them. Error handling is quite poor in most Android applications. And then we found the one memory safety issue in the Instagram imaging app that I showed before. That was MALintent. I encourage you to look at the paper for more of the nitty-gritty details. This was as short as it can be. Thank you.
Thank you. Any questions? Please come to the microphone. I guess while we wait, I have a question. So I noticed that there are a lot of crashing bugs.
Mm-hmm.
Do you have any clue? Like, are those? I guess a subset of them potentially memory safety bugs too?
So most of them are not memory safety issues. These are like null pointer exceptions, index array out of bounds in the Java side. So yeah, the Java side usually, they're not exploitable in any way except just denial of service on the app.
Okay, thank you. Right. No more questions. Let's thank the speaker again.